First question we are going to discuss is design a Turing machine to recognize the given language, that is equal number of A's and equal number of B's. So the strings that are accepted by the language are AB, AA, BB, AAA, BBB and so on. So the example string we are going to take here is AAA, BBB. So first the initial state Q0, the input would be A. So when the first input is A, the A should be changed to X and it should move towards right. So the finite controller points to A. And after changing A to X, how many ever A's are encountered, they should be the same. So A stays as A and move towards right. So when the first B is encountered, the B should be changed to Y and move towards left. It goes to Q2. And now, so while moving towards left, so keep the A's as A and move to left. And when the X is encountered, it should move again towards right side. X, keep it as X and move towards right. And then we get the input the next A, and then again it is changed to capital X and then move towards right. And the next A is encountered, it stays as A and move towards right. Then here we change the B as Y. So when Y is encountered, it doesn't change and it moves towards right. Then when the next B encounters, it is changed to Y and moves towards left. So here we are encountering a Y. Keep it as Y and then move towards left. And in the same process, again it comes to state Q0 because it is encountering an X here. Then again it moves to right. The A is changed to X, and then Y's remain the same. And then when B is encountered, it is changed to Y. And then now in the process of moving again to left side, there are no A's or B's here. And so when the X here is encountered, it moves again towards right. So when Y is encountered, it goes to state Q3, keeping Y as Y and moving towards right side. And how many ever Y's are encountered, they are not changed, and the finite controller moves towards right. And there are blanks here. So after Y's, when the blank is encountered, it goes to the final state to Q4. When the input string reaches the final state, then that string is accepted by the given language, that is equal number of A's and equal number of B's. So the state table for the Turing machine is here. Inputs are A, B, X, Y and blank state. So first state Q0, when the input is A, it is going to state Q1, changing it to X, and the finite control moves towards right. And the other input for Q0 is capital Y. It goes to state Q3, keeping it as y itself and moving towards right. There are no other inputs for state q0. For state q1, the inputs are a, going, there's a self loop q1, a and right. The next input b, it goes to q2 state, changing it to y and moving to left side. There's no x input for y, it has self loop, so q1, y, and it's moving towards right. For state q2, the inputs are first a, it goes to q2 itself and it doesn't change, remains as it is and moves towards left. And input x, it goes to state q0, there's no change, the finite controller moves towards right. And when the input is y, there's a self loop q2, y and left. For state q3, the inputs are y, there's no change in the state and it moves towards right. And there's input blank, it goes to state q4, no change, and right. And for state q4, that is final state, there are no inputs. So this is a Turing machine for equivalent of A's and B's, and this is a state diagram. The next question we are going to discuss is Chomsky hierarchy. So Chomsky hierarchy on languages, there are basically 4 types: type 3, type 2, type 1 and type 0. The first one, we shall start from the center, type 3. Type 3 is regular grammar. So for regular grammar, the production rules are of the form alpha tends to beta, where alpha takes a non-terminal and beta takes a non-terminal followed by terminal star, that is left linear grammar, and a terminal star followed by non-terminal, that is right linear grammar. So in regular grammar, there are basically 2 types of grammars, left linear grammar and right linear grammar. So the recognizer for regular grammar is FSM, that is finite state machines, that include DFA, NFA, Mealy and more machines. So for every NFA there exists an equivalent DFA. This, and next one is type 2, that is context free grammar. So context free grammar, the production rules are the form alpha tends to beta, where alpha is a non-terminal and beta is V union T whole star. So all the regular grammars are also context free grammars, but the vice versa is not true. So the recognizer for context free grammar is push down automata. So for every non-deterministic push down automata, there is no equivalent deterministic push down automata. The next one, type 1 grammar is context sensitive grammar. So context sensitive grammar, the production rules are the form alpha tends to beta, where the length of alpha is less than or equal to length of beta. All the context free grammars are also context sensitive grammars, and the recognizer for context sensitive grammar is linear bounded automata. The next type of grammar is type 0. Type 0 grammar is unrestricted grammar. And the languages that are given by unrestricted grammar are recursively enumerable languages. The recognizers for unrestricted grammar are Turing machines. So for every non-deterministic Turing machine, there exists an equivalent deterministic Turing machine. So all the regular grammar, context grammar, and context sensitive grammar all come under unrestricted grammar. And this is a diagram for Chomsky hierarchy. The first one is unrestricted grammar. Unrestricted grammar recognizes Turing machine. The next one is context sensitive grammar. The recognized is linear bounded automata. Type 2 is context free grammar. The recognized is push down automata. Type 3 is regular grammar. The recognizers are finite state machines.